So chapters 6 and 7 are combined and then split up into an inorganic chapter and an organic chapter. So we equate inorganic with metal, non-metal bonds, so ionic bonds, and then organic we do non-metal, non-metal, so covalent or molecular. So for this unit, we're going to focus on inorganic, that's ionic compounds, chemical bonding. So just as a little overview, we have different types of bonds. Here in this picture, you are seeing an ionic bond where we actually have electrons that are leaving one atom, going to another atom, and creating a compound. This is MgCl2, 1 magnesium, 2 chlorines. If you take a look at the periodic table, magnesium is in group 2, so it's a metal, and chlorine is in group 17, it's a non-metal, so that's a metal-non-metal bond, and it's ionic. We actually have the transfer of electrons there. Covalent, which is this one, they share electrons, so that's what you see here is 2 electrons being shared, one from one chlorine and one from another chlorine. We have other types of bonds. Metallic is another one. Network solids is another one. Network solids is like when you take a nonmetal like carbon and you bond it to itself. It almost looks like an ionic bond because it has like that kind of like crystal structure, but it's made of a non-metal carbon. So like that's what diamonds are made out of. That's a good example of a network solid. It's very strong, has that crystal structure. So ionic versus covalent, we saw it in that last picture, but here you can see it sort of visually too. We have positive and negative charges because an electron left one atom and went and joined the other, giving one a positive and one a negative, and that's how they stay stuck together, is because positive and negative attract, right? Opposites attract. So in an ionic bond, they stay stuck together because some of the molecules are positive and some are negative. In a covalent bond, the electrons come together to be shared. That's how a covalent bond stays together, is because those atoms are sharing electrons. So just again, as an overview, ionic is metal and non-metal. Covalent is non-metal and a non-metal. And then metallic is just a bunch of metals. So this is when you get a like a solid piece of gold, right? That's a gold atom bonded to another gold atom. And so forth. We'll look at that at the end of this because it doesn't really fall into ionic or covalent, but we are going to talk about it in our inorganic chapter since it doesn't contain nonmetals. So for all atoms, this applies to both ionic and covalent. This just applies to bonding in general. We have like levels of positive and negative. So if it's an ionic bond, that's a metal bonding with a non-metal. They are giving up, I missed an N in there, they're giving up electrons and gaining electrons. So we get a full positive and a full negative charge. That's ionic. Then we have, these are differences in electronegativities over here, right? Differences in electronegativities. So if our electronegativity is high, right, 3.3 to 1.7, that's an ionic bond. We can also tell on the molecule because it's a metal and a non-metal. Here, 1.7 to 0.3, if our electronegativity difference is between that range, we call it polar covalent. So that's when two atoms are still sharing electrons, right? They're still sharing 2 electrons, but maybe one of them is more electronegative than the other. So one of them holds on to those electrons a little tighter. It might look something like this, maybe something like that, where it takes the electrons longer to get around this one, and then it kind of goes around that one quickly. That would give us a positive or a partial negative and a partial positive. So that's what polar covalent means. It means that we have our poles, right? We have our positive pole and our negative pole, but they are still sharing electrons. So that's polar covalent. And then non-polar covalent, this last little part in here, the 0.3 to 0, those are when they're essentially sharing electrons evenly. So when they have really close electronegativities, they're pulling on electrons at the same strength, I guess you could say. Therefore, they're not considered to have a partial positive or partial negative charge. This happens for like diatomics, so things like chlorine, Cl2, when it's in its solid, or when it's in its gas form. I meant its elemental form. It is a gas, and we have the chlorine bonded to another chlorine, and they're going to share those two electrons equally because it's the same element, therefore it has the same electronegativity. So that would be an example of nonpolar covalent. No partial charges. So we have full charges, partial charges, and no charges, depending on where it sort of falls in this ionic polar character. I just liked this because it was a good representation. If you start Googling, you are going to see this number here. So on this picture, it was 0.3. That's the same one in your book, and that's the one that we're going to use as the one from your book. If you start Googling, though, you might see it 0.4. There's other places where you might see it 0.5. That non-polar to polar line, it's not that it shifts, it's just that when we get to differences in electronegativities, we can see very temporary partial negative and partial positive changes right when we get around to these numbers. So we're going to go with 0.3. If it was a test and it was 0.4, you would call that polar covalent. But if you start Googling, you will see other ones. I picked this picture, though, because I really liked this visual here. That's what I was trying to draw on the other side. Where ionic, we have the negative and the positive. In polar covalent, we have these partials. And then in non-polar covalent, there are no partial charges. So if you want to take a pause here and try and do this on your own, you can. It says what type of bonding would be expected between these pairs. So if you want to pause and go through this, you can. If you just want to watch me do it, you can do that too. So our first one is oxygen and nitrogen. So oxygen is 3.5 and nitrogen is 3, which gives me a 0.5. So we would call that polar covalent. Sodium and chlorine. Well, sodium is a metal, so I can already tell you it's ionic, but if you want to do the math, you can. Chlorine is 0.3 and sodium is 0.9, so that gives us 2.1. It is ionic. But it was a metal and a non-metal, so I can already tell you it's fully ionic. When you're subtracting electronegativities, you should never get a negative number. You're always just... If you get a negative number, make it positive. We're looking for the difference, not necessarily a positive or negative value. We're just looking for the difference between the two. Let's see. Bromine is 2.8, and I'm going to subtract iodine, which is 2.5. That gives me 0.3, so that's non-polar covalent. Hydrogen is 2.1, and fluorine is 4, so that gives me 1.9. So that is actually ionic character, but because it's a nonmetal and a nonmetal, we do call that polar covalent. But if you go back and look, it is ionic character. It'd be right here, 1.9. And then last is aluminum, which is 1.5, and chlorine, which is 3.0, giving us 1.5, which is polar covalent. Oh, this is supposed to be an arrow. These are both supposed to be arrows. So based on their electronegativities, like how strong they would hold on to electrons or how easily they give up electrons, all of the trends, when we're making an ionic compound, they have full charges, therefore, based on where they are on the periodic table, they're going to have similar charges. For example, everybody in group 1 has one valence electron. They're all going to give up one, so they're all going to have a +1 charge. So when they're bonding and it's a metal, it's always going to give up its electrons. How many? Well, group 1 is going to give up 1, group 2 is going to give up 2, and so forth. When you have a nonmetal and they're accepting electrons from the metal, again, you're going to get halogens with a -1, oxygen's group with a -2, and then nitrogen's group with a -3. These are only for the nonmetals, which is why all of this is blocked out, is because those are metals and metalloids. These are the only metals that are not group 1 or 2, where we do know the charges, and those are 5 that you should commit to memory. So if I was going to write a formula, I would say calcium, for this example here, I would say calcium has a +2 charge. I know that because it's right here. It has a +2 charge, and it's going to bond with chlorine. That's an ionic bond, therefore I have charges. Chlorine is -1, and I have 2 of those. This little 2 here means that I have 2 of those. So if I was going to break those down into their ions, I would call them aqueous because that's what we call ions. They're not solid or liquid. They're just aqueous, which means dissolved in a substance. Typically that substance is water. But those are the 2 ions created by calcium chloride. So once that exchange in electrons takes place, I said earlier that the positive and negative attract. You can see in the example here, we have negatives attracted to positives. That attraction we call an electrostatic force. It's just what holds an ionic compound together. So Lewis structures show how we, like what the electrons are actually doing, like what's taking place. So I'm just going to pick 2 elements. Why don't I pick sodium? And I'm going to pick oxygen. Sodium and oxygen. So based on their position on the periodic table, I'm just going to go back. I think we had one here. Yeah, sodium is right here with 1 valence electron. I'm just going to write valence electrons up here so we remember. 1, 2, 3, 4, 5, 6, 7, 8. So sodium has 1 valence electron. So over here, I'm going to write 1 valence electron on my sodium. Oxygen has 6 valence electrons, so I'm going to go ahead and draw 6. When you're doing valence electrons for Lewis structures, you want to pretend that there's a little imaginary box around your element, and every side of that box is going to get 1 electron before any side gets a second. What that allows us to see is how many bonding electrons there were. If you didn't do that, if you went 1, 2, 3, 4, 5, 6, that shows me 3 lone pairs and no bonding electrons. Bonding electrons are single electrons. So what you're telling me by drawing it like this is that it cannot create any bonds, which is not true. Oxygen can create 2 bonds. I have a bonding electron here and a bonding electron here. Sodium can create 1 bond. I have 1 bonding electron. So this electron here is going to leave and join that electron. If I just maybe make them different colors. So it's going to join that electron. Well, I still have this bonding electron down here on the bottom of oxygen that needs a buddy. So what's going to happen is a second sodium is going to come in and give it another electron. So when it does that, it leaves sodium, whoopsie, not +2, with a +1 charge, and I have 2 of them. It leaves oxygen with a -2 charge, right? It gained 2 electrons, so it has a -2 charge. So when I write this formula, I say how many sodiums do I have? I have 2. How many oxygens do I have? I have 1. So for sodium oxide, that is the formula. When you are doing ionic compound Lewis structures in your notebook, this is what I would like to see. I would like to see first what the electrons are doing, second the ions, and then third the chemical formula. So I was talking earlier at the very beginning about other types of bonds, network solids and metallic bonds. And I said network solids kind of look like ionic bonds, and this is why. So when we have these positive and negatives, so here with cesium, we have a positive charge in the middle, and then these are all chlorine, so they're all negative charges. And what happens is they kind of build this crystal structure here where we have a positive and a negative and 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 a positive. And they build these like strong crystal structures. So this is why ionic compounds tend to have like such a high melting point, is because these structures with these electrostatic forces in between are very, very strong. Network solids do that same thing, only it's not positive negative. It's just the same element bonded to itself. We call these the compounds We'll call that a formula unit. So I have one formula unit of CaF2, calcium fluoride, or you could say 1 mole as well, but when you're asked to calculate a formula unit or something like that, you would calculate for 1 calcium and 2 fluorine. You guys already calculated formula mass. You're doing that for 1 formula unit, which is, again, just the symbol, and it just represents the ratio between the 2 elements, between the metal and the nonmetal. So here, my ratio for calcium is 1 to 2 fluorine. So that's considered 1 formula unit. If I wrote it like this, right, I have 2 formula units. So a formula unit is just the compound, and it demonstrates the ratio between the metal and the nonmetal. And metallic bonding, our last type of bonding. So metallic bonding is just kind of what it looks like here. You have a lot of positives all shoved in together. So when you have something like solid gold or solid silver or solid zinc or solid copper, like any of the metals, when you have a solid metal, this is how it bonds to each other. They pack in really, really, really tightly together, and then they have sort of what we call a flow of electrons. So this electron here is not actually on one of these nuclei. It kind of like flows in here, which is why metals can conduct electricity. It's because those electrons can sort of like flow and move freely. We call it a sea of electrons. And so there's a proper amount. There's the amount of electrons you need in order to neutralize the amount of protons, but they're packed so tightly together that they have that free movement, which is why, again, they can conduct electricity. So just as a little overview, there are 3 main types of structures. So ionic, which is metal-nonmetal, covalent, which is nonmetal-nonmetal, and then metallic, which is just like a metal atom that's repeated. For covalent, we have network solids, which are like what I was saying about carbon bonded to itself to make diamonds. And we also have covalent molecules, which are non-metal, non-metal. And then we have bigger molecules, which are like the bio stuff. So this unit, we're focusing on ionic, but you're going to see this picture again when we talk about covalent as well, just because I feel like it's a good way to classify it. That's it for these notes. Please let me know if you have any questions.